Unit 4, the third section. All right, so you may have noticed by now that there's been a lot of repeating over and over and over again. 1s2 keeps getting repeated over and over again. And so what we're going to do in this very end here is we're going to distinguish between the noble gas elements and the others. Now, if you were to go through the electron configurations for the noble gases, which is group 8A or group 18, you will notice that they always have a completely filled S and P subshell in whatever period they're in, so whatever row they're in. So in the first shell is completely filled 1s. In the second shell it's completely at 2s 2p6, 2s2 2p6. In the third shell it's 3s2 3p6. In the fourth shell, even though it's more complicated in the middle, they still complete the fourth s's and p's, 4s2, then 3d10, and then 4p6. So there's always 2 s's and 6 p's in whatever energy level that noble gas is in. We call this a closed shell because the next electron would have to be gone to the next highest energy level. So after argon, for example, which is 3p6, even though there are 3d orbitals, before we can get to them, we have to go to the fourth shell, which is the highest shell. So the noble gases complete the energy shell. They complete, we call them a closed shell. And so it turns out that the only electrons really involved in chemical reactions are those that are in the highest energy shell. We also call that the valence shell. So the highest energy shell is called the valence shell. Anything below those electrons in those closed shells are called core electrons, and they're kind of locked in, and so they don't really take part in any kind of chemical reactions. And so what we're going to be able to do is write abbreviated electron configurations called noble gas configurations, where we're going to represent the core electrons just by one noble gas. And so it's not too hard to follow. So let's look at magnesium and neon side by side. So notice that neon, 1s2, 2s2, 2p6, and then magnesium, 1s2, 2s2, 2p6, 3s2, are identical except for those last two electrons. Since neon is a noble gas, we have a closed first shell and a closed second shell. So we can actually write them, you can see it here, we can put neon in brackets, and we only use noble gases again. So neon being a noble gas, you can do that. So we put neon in brackets and we just say, okay, magnesium has everything neon has plus a 3s2. So we put the brackets neon and then write 3s2. And that is called the noble gas configuration of magnesium. So instead of writing the whole thing out, all we have to do is put the last electrons that show up after the previous noble gas. All right, so let's look at gallium. Gallium, you notice, ends with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. Now don't get too confused, because the noble gas that or the closed shell, the highest closed shell would be the third shell, because it has its complete S's and P's. So even though we're in the fourth shell, and even though we have D's, because the S's and P's, we want to look for the S's and P's in the highest energy level that are totally full. So argon is the same as 1s2, 2s2, 2p6, 3s2, 3p6. So argon is the noble gas with the closed third shell. And then we just put everything that comes after argon, 4s2, 3d10, 4p1. If you want to, you can draw out argon, and you'll see that that ends in 3p6. Now, gallium is before krypton, and so we can't use krypton as our noble gas because we don't have enough electrons to get there. So now also notice the highest energy electrons in gallium are the 4s2, 4p1. They're in the highest shell, which is the fourth shell. So even though those 3d electrons show up, they're in the lower shell. So the highest energy electrons are the fourth shell electrons. And so we say there are 3 electrons in that highest shell. Previously in magnesium, we would say there's 2 electrons in the valence shell, or the highest energy shell. Sometimes in other cases you'll see the 3Ds and 4Ss switched, and so you can see here argon 3D10, 4s2, 4p1. So now you see that only the 3 fourth shell electrons are the highest energy levels. And I don't care which way you write them. You might see them one way or the other. I usually like to put the 3Ds after the 4Ss because that helps you remember the order that they fill. But it doesn't matter which way you put them. But notice those that bold on the bottom, you only use noble gases in the brackets. That's why it's called a noble gas configuration. So I think on the next slide you'll see how you can look at the periodic table and figure it out. All right, so if you look at the periodic table, let's say for sulfur. So find sulfur, which is element 16. It's in that purple box, or sort of a dark magenta box. And what you want to do is look at the noble gas on the row above it, because that is the last completed shell. So notice that for sulfur, neon is the noble gas that's complete. So sulfur has electrons past neon, but we put neon in brackets. Then we follow what comes after neon, and before we get to sulfur, well, now we have to jump down to row 3, and notice that after neon there's 3s2, and then there are 3p4. Sulfur is 3p4. So we put everything that comes between neon and sulfur after the brackets in neon. So the noble gas configuration for sulfur is neon in brackets, 3s2, 3p4. Technetium, notice that technetium is in period 5, so we go back to period 4 to get our noble gas. So krypton is what we put in brackets. Then what comes after krypton? 5s2. We're still not to technetium yet. And then what comes after the 5s2? Those are the 4Ds. How many are there? Well, yttrium is 1, zirconium is 2, niobium, Nb is 3, Mo is 4, technetium, then Tc is 5. So it's the 5th one, and so we would write krypton, 5s2, 4d5. So you might want to go back and look at some of the other examples, or practice a few. There is a practice sheet in your content area, and it's something that's optional, but you can write electron configurations, the longhand, and I've given you the answers to them. And then I also have some examples of writing noble gas configurations for you to practice, and then there's an answer key for that. So you might want to practice that a little bit and check yourself. All right, so let's do a few examples here. Write the noble gas configurations for the following elements. You might want to have your periodic table in front of you, because it's really hard for me to show you this without the periodic table. But iron, notice that iron is in row 4, so we have to go back to row 3 noble gas, which is argon. And then after argon comes the 4s2. And then iron is in the 3Ds, and it is 3D, 1, 2, 3, 4, 5, 6. So argon, 4s2, 3d6. All right, how about selenium? Selenium is in the 4th row, so we have to go again back to the 3rd row noble gas, which is argon. Then everything that comes after argon and then up until selenium and including selenium would be 4s2, 3d10, all the D's are filled, and now selenium is in the 4p's, and it's 4p4. So argon, 4s2, 3d10, 4p4. All right, aluminum. Aluminum is in the third row. So we have to go back to the second row noble gas, which is neon. So neon goes in brackets. After neon is 3s2, and then aluminum is 3p, and it's the first one, so it'd be 3p1. Neon, 3s2, 3p1. Okay, finally cesium, Cs. That's all the way down in the sixth row. This one's actually an easy one, even though you might think, oh, it's way down there. Cesium, you have to go back to the fifth row noble gas, which is xenon. And then what comes after xenon and including cesium? Well, it's just 6s1. That's cesium is the next element, so it would just be xenon 6s1. All right, so again, now you can see what are the valence electrons. The valence electrons, remember, are the highest energy electrons. And now that we've written noble gas configurations, we can see pretty easily which one are the highest energy electrons. Now, the really nice thing, though, is that notice that everything that's in the same column has the same electron valence shell configuration. So lithium ends with 2s1, sodium ends with 3s1, potassium ends with 4s1, rubidium ends with 5s1, and cesium ends with 6s1. And so when you start to see that the valence electrons for group 1A all have one electron in their highest energy level, you can start to see why they all act alike. They act chemically, they act very similarly, and we'll see that more in future chapters. But with all of them having one electron in their outer shell, they're going to start to act alike. And then you can see group 2A all have 2 electrons in their outer shell. Group 7A, if you look at, or group 17, if you look at fluorine, chlorine, bromine, iodine, and astenine, At, notice they all end with S2P5 in their highest energy level. So they all have actually 7 valence electrons. So just a summary, and this is why I like using the A's and B's, because it sort of helps you remember. Group 1A has 1 valence electron. They all end with S1. N just represents which shell we're on. So it's 2 for lithium, 3 for sodium, 4 for potassium, etc. All group 2A elements end with NS2, 2s2, 3s2, 4s2, whatever. Group 3A elements all have 3 valence electrons. They end up with S2P1. So aluminum, for example, ends with 3s2, 3p1. Gallium ends with 4s2, 4p1, etc. Group 4A elements have 4 valence electrons, and you can see they end with S2p2. Group 5A elements have 5 valence electrons. Group 6A elements have 6 valence electrons, S2p4. Group 7A all end with S2P5 with 7 valence electrons, and then all group 8A elements, except for helium, have S2P6. And so now we're back to a closed shell. And then after group 8, what happens? They cycle back to 1. Now the transition metals are going to be different because they're in the D, and it does get much more complicated, and we're just not going to worry about them in this class. So again, I said this earlier, because the valence electrons are the furthest away from the nucleus, they are the least strongly held. They're very far away. They're not held very, very well. And so those are the ones that do all the chemical reactions, like I said earlier. They're the important ones in determining the properties of the elements. And so when elements have a similar electron configuration in the valence shell, they'll have similar properties. So that's why everything in the same column tends to act very similarly. And again, we'll see that in future units. All right, so Using N to represent the number of the outer shell, write the general outer shell configuration for the elements in group 6A. All right, well, remember that group 6A, or group 16, has 4 electrons in the P's and 2 electrons in the S's. So they all have 6 valence electrons. They all have 2 in the S's, so NS2, and then they have 4 in the P's, so NP4. NS2, NP4 is the general configuration. All right, how many electrons are in a tin atom? Well, tin, you may have a hard time finding it, but tin is SN. It's element number 50. Give the number of electrons in each shell. All right, so you can kind of do it. We know the first shell has 2, the second shell has 8, the third shell has 18. Now the fourth shell has S's and P's, and then also D's, so again 18, and then the fifth shell has S's and 2 S's and 2 P's. So 4 electrons in the fifth shell. And notice that it's in group 4A, so it has 4 valence electrons. It has the configuration 5s2, 5p2. Even though the 4d's come in between, remember the 4's are a level lower, so we only count the fifth shell electrons, and so it has a valence of 4 valence electrons. Now, the last thing we're going to do is we can classify elements using different ways, and we've already seen a few of these. And so we're just going to look at the periodic table and learn different ways of classifying elements. So you can see here we're going to do it by the distinguishing electron, which is what we've already been doing. We're going to classify them by status, as you'll see in a minute, or as metal or nonmetal or metalloid. Okay, so let's look at, first of all, distinguishing electron. We've already seen this picture. So we can look at an element and we can decide what is its distinguishing electron. Is it an S, a P, a D, or an F? So if you're looking at, say, phosphorus, which is element 15, what's its distinguishing electron? Its distinguishing electron is a P electron. It's in the P block. So that's pretty easy because we've already done that. Another way that you can look at the periodic table is by type of element. So the representative elements is, or sometimes we call them main group. Main group or representative mean the same thing. They are actually all the elements that are in groups 1A through 8A, or columns 1 and 2, and then 13 through 18, depending on which system you use. So the representative elements basically are the S block and the P block elements. So those are representative or main group. Then all the D block elements are called transition metals. And then finally, all the F block elements are called inner transition elements or inner transition metals. And that brings us to the final characterization or way to organize, and that is by metal or non-metal. So this is a nice little periodic table. All the red elements are non-metals. Notice that there's a little orange zigzag line going from left to right, sort of starting at boron and then zigzagging all the way down to PO number 84. That is the technical dividing line between metals and nonmetals. So if you just want to say, is it a metal or a nonmetal, everything to the right above that line is considered a nonmetal, and everything to the left below that line is considered a metal. However, you'll notice that we have a third characterization, and that is called a metalloid. And so those elements in green that sort of border the orange line we call metalloids. So notice the blue ones are metals, the red ones are nonmetals. Hydrogen sort of acts by itself, and so it's actually a nonmetal. And then the green ones are metalloids. So I think one of your homework problems has you just tell me, you know, that element, what is it? Is it a S block, P block, D block? Is it a metal, nonmetal? Is it a representative, etc.? So now you can do that by looking at these three periodic tables. All right, so what is the difference between a metal and a nonmetal? And you probably already kind of know this because you know what a metal is. Well, most metals have the following properties. They have high thermal conductivity. That means that they transmit heat very easily, as you probably know if you ever touched a hot frying pan. They have high electrical conductivity, which means they'll let electricity flow through, which is why most wires in our household are metals, copper wire, etc. They are ductile, which means that you can draw them out into wires. And they are malleable, which means that you can pound them into flat sheets like aluminum foil. And they also have metallic luster, which means they tend to be shiny. Most nonmetals have properties that are opposite of those. So generally, nonmetals tend to be gases. A lot of the nonmetals are gases. Some of them are liquids, but mostly gases. If they are solids, they tend to be powdery or brittle, and they don't conduct heat. They don't conduct electricity. You can't make wires or flat sheets out of them. And like I said, most of them are gases. Now, metalloids are elements that are sort of halfway between. They're sort of metal. They have some metal properties and some non-metal properties. They exhibit some characteristics of both. And an interesting thing, metalloids, some of the most important metalloids that you'll find are silicon and germanium. And you may have heard of Silicon Valley. Silicon Valley, which of course is where they did all the computers, or they still do, but the reason why it's called that is because silicon is used in all computer chips, and the reason why it's so good at computers is that it is conductive. It will conduct electricity and heat, but yet not so much that it shorts itself out, or you know, like a true metal wouldn't be able to conduct it would conduct too much electricity. And so silicon and germanium, which are used in computers, are sort of halfway between metal and nonmetal. If you look at the periodic table, you can actually see, notice that as you go from right to left, metallic character increases. So if you're looking like, let's say at row 3, sodium is much more metallic than argon. Argon is a nonmetal. It's a gas. It's a noble gas, in fact. It is non-metallic, but as you go from right to left, from argon to chlorine to sulfur to phosphorus, you keep getting more and more metallic. And so if I asked you which is more metallic, sodium or magnesium, you would say sodium because it's further left. Also, metallic character increases going down a column. So if I asked you which one is more metallic, cesium, number 55, or sodium, number 11, cesium would be more metallic because it's further down the column. Now, sometimes it's hard to compare something that's not in the same column or the same row, so I wouldn't ask you that, but just within the same row or the same column. Another thing that you can understand from looking at the periodic table is atomic radius. The radius of an atom is just defined as the distance from the center of the nucleus to the highest energy electron. So what's the distance from the center to the outside? One thing that you'll notice, you can see the picture here, the graphic. As you get larger, as you go down a column, you can see that clearly they're getting bigger and bigger and bigger. We're adding more and more levels of electrons, second row, third row, fourth row. So they're getting bigger and bigger and bigger. So you can see hydrogen's very small, then lithium is bigger, sodium is bigger than that, potassium, rubidium, cesium. And that should make sense to you as you're adding more and more levels. It should be getting bigger and bigger. And the same thing's true if you look at group 8A. Helium is the smallest, and then neon gets bigger, argon, krypton, xenon, and radon. Any of the rows as you go down should be getting bigger and bigger. Now, the one trend that you might not predict is you see that actually lithium, which is over there on the left-hand side, is quite a bit bigger than neon. And in fact, the atomic radius will increase as you go from right to left. So notice that all of those elements there in the right-hand side are smaller than the ones on the left-hand side if you're going on the same row. This may seem odd because you think, well, I'm adding more electrons, but keep in mind that you're adding more electrons to the same shell. And so if everything else was equal and you were adding to the same shell, then they should all be the same size because you're putting electrons all at the same distance. But what happens is as you go from left to right, you're increasing the number of protons in the center. And so more protons pull a little bit stronger on the electrons and shrink them in, make them a little bit tighter. And so, in fact, the atomic radius gets smaller as you go from left to right. So it's a little bit odd, but you can just remember the trends. All right, there's one more trend that we want to look at, and that is ionization energy. So first of all, what is an ionization? First, ionization. Well, it's defined as the amount of energy you need to remove an electron from an atom. So in other words, how hard is it to move an electron? So high energy to remove an electron would be really hard. If it's low energy in order to remove an electron, that would mean it's pretty easy to do. So notice that the periodic trend, if you go from left to right, you increase ionization energy. As you add more electrons to the outer shell, it's going to be harder and harder to pull electrons away. So as you go across from left to right, ionization energy will increase. It's harder to pull electrons away. As you go from the bottom to the top, notice that the arrow is coming up. It's easier to pull electrons away from the much bigger elements than it is from the smaller ones. And that's because in the big elements, the electrons are far away from the nucleus, not being held so tight, and so it's easy to pull an electron away. Whereas the smaller elements have the electrons really close to the nucleus, and so it's much harder to pull them away. All right, so I messed up. We have one more trend to look at, and that is electron affinity and electronegativity, which are very similar to each other. They're slightly different, and electron affinity is how much energy is required to add an electron, and electronegativity is more like how much does an atom want electrons when they're in a when they're bonded to something else. How much will they pull on the electrons? And so notice that the trends are actually very similar to the previous one. And it should make sense in this way. So if you go from left to right, notice that electron affinity and electronegativity increase, meaning that they really like electrons. They're willing to add another electron, or they're wanting to hold on to electrons. And that sort of makes sense from the previous slide where we said that it was increasing ionization energy. So if they really want to hold on to the electrons, that means they're not going to be willing to give them away. And so it's really kind of the same way at looking at it. The electron affinity means how much does it want an electron, and the ionization energy means how much is it willing to give it away. So if it's very high ionization energy, it also has high electronegativity because it's willing to hold on to electrons really tightly. And then also going from the bottom to the top, as the electrons are closer into the nucleus, they're going to be held tighter, and so they'll be more willing to add an electron or to hold on to their electrons. All right, this one, electronegativity especially, will show up in some other units down the line. So this would be the main one to understand, that as you go from left to right, they really want to hold on to their electrons. And as you go from the bottom to the top, again, they really want to hold on to their electrons. They really very much like electrons. All right, so that is the end of Unit 4. I hope you enjoyed it.